Today we're going to talk about another part of a quantity, and that is its direction. We learned that there are four different parts. There is the value, there is the unit. Today we're talking about the direction, and our final part will be regarding uncertainty. Now, there are lots of quantities that we call vectors. That is, that their direction is important. We can't just ignore it. One of the most common is velocity. If something is moving west, it's not the same as if it's moving east or if it's moving northwest. Displacement is similar to distance, again, but that specifically has to do with if it was moved to the left or to the right, or if something moved up or down. Forces and momentums are other quantities where the direction is important. Now, there are many different ways of describing the direction of a quantity, and none of them is any better than the other. We simply use whatever is most convenient for the particular situation. A lot of times that's as simple as just using a negative sign. In kinematics, we tend to use negative signs quite a bit to represent down. For instance, negative 9.8 meters per second squared is the acceleration that most objects experience, and that is downward, not upward. In other cases, it's simple enough simply to state the direction, 40 miles per hour west versus 50 miles per hour east, or 50 pounds upward versus downward. In other cases, we would indicate the direction by using a tool called a vector. A vector is just an arrow that points in a specific location, and its size is supposed to be drawn proportional to how big the value is. So here's an example of a vector, and maybe this vector represents a particular speed of 10 miles per hour. And if I have another speed of 4 miles per hour south, then I would draw it smaller and aiming straight down. Now, since vectors are what are most unfamiliar probably with us, we're going to do a couple different examples of how you can do arithmetic with vectors. One of the simplest things you can do is to just draw a quick little picture. If you don't need a specific number, you can add vectors simply by drawing them end to end. If I wanted to add these two vectors together, one thing that you can do is you can move the vectors around and place them end to end. So if I simply move this vector from here to here, it still means the same thing, still the same distance. But now I can draw what's called a resultant vector, and that is the total of these two, or the sum, or our answer, if you will. And that goes from the tail of one vector to the head of the other vector. So these two vectors, when I add them together, equals this vector. Again, this particular tool is simply to get kind of an estimate. We don't actually know how long that vector is or at what specific angle it is, but it's sufficient to know that it's pretty long, longer than either of the originals, and it's almost exactly east. Something cool with this method is that addition is commutative, which means that it doesn't matter what order I add these two vectors together. I chose to put the long one at the end of the small one, but suppose I did it the other way. Suppose I had put the small one at the end of the long vector, and suppose now I draw a vector from the big tail of this one to the head of the other one. Notice that this sum and the sum we had before are essentially the same. Now, most of the time, we need to be a little bit more specific than simply drawing a little picture. We want to know the exact sum of them, or the exact angle of the two. And in order to do that, we need to learn two specific tools. We need to learn how to break a vector up into what are called components, and we need to learn how to recompose a vector from components. To break a vector into components, we need to use some right triangle trig. So it might be helpful for you to have some of these formulas from trig handy. This is sine and cosine and tangent definitions, which is often summarized in the Indian name SOHCAHTOA. So if you don't have those memorized, I would suggest you write them down and have them available to you on a note card or so on. So let's use those trig definitions to answer a specific question. Suppose I had a speed of 20 meters per second, and I know that the angle is 24 degrees. I'd like to figure out how much of this speed is due horizontal and how much of this speed is due vertical. To do that, I need to solve this particular triangle. Let's call this x and y for now, and solve this using the triangle trig. If we look at the x value, the x and the 20, which is what I know, this is the adjacent side to the angle, 24, and 20 is the hypotenuse of this right triangle. And so I can use the cosine function, cosine of our angle, remember, is adjacent over hypotenuse. And so if I get specific, the cosine of 24 degrees is equal to x, which is the adjacent side, divided by 20. And to solve a problem like this for x, I would suggest we multiply both sides by 20. That gives us 20 times the cosine of 24 is what x is. So let's get out a calculator and answer that. Before I begin, make sure that you are in degree mode. If you're in pre-calc or calculus as well as physics, you will probably be in radians for that class. You'll want to make sure you are in degrees anytime you're in physics. So that's simple enough. Just go down to radians and degrees and make sure you're on degrees and hit enter. And now we can type in 20 times the cosine of 24. And we get 18.27. Let's round that to 18 meters per second. And to figure out the vertical component, we can do the exact same steps as we did before, only notice that y is opposite the angle instead of adjacent. And so to calculate y, we should use the sine. The sine of our angle, which is 24 degrees, is equal to the opposite, which is y, divided by 20. We can solve this equation the same way we did the last one by multiplying both sides by 20. And if we go back to our calculator, we can type the same equation in as before. If you hit second, enter, that brings up the last equation. And really the only thing we need to do here is to change this to be a sine instead of a cosine. And we can enter that, and we get 8.13. And so we'll say that that is 8 meters per second. The next skill is to recompose a vector from components. And for that, we are again going to borrow some equations from trig. Specifically, we're going to use the Pythagorean theorem, and we're going to use the tangent definition, but usually we'll use the inverse tangent. So let's answer a specific question. Suppose I've got two vectors, 30 meters to the east and 18 meters north, and I would like to add these two vectors together. To figure out the length of the resultant vector, this is just two sides of a right triangle, and so I can immediately use the Pythagorean theorem. Pythagorean theorem is that 30 squared plus 18 squared should be our hypotenuse squared. And so to solve this, take the square root of both sides. And we can calculate this. The square root of 30 squared plus 18 squared is about 35. And to find the angle, we're going to use the fact that we know the opposite and the adjacent sides of this angle. And so we'll use the tangent rule. Tangent of theta is 18 over 30. And to solve for theta, we need to take the inverse tangent of both sides. And that would give us theta equals the inverse tangent of 18 over 30. The inverse tangent is second tangent of 18 over 30. And just by looking at the picture, it would be something like 20 degrees. So when I enter it in, it looks like 30. So I underestimated a little bit. So theta is approximately 31 degrees.